It's an experimental contribution more because it has been funded by a program by EDF as the electricity operator in France, and also by LabEx, which operates on smart vehicles and renewable energy. But it underlies specific fundamental features about B-level programming. And I'm going to talk a little bit about them. And because it is an experimental work, it has been involving several players. I forgot to mention them, but you see we are several people who have been, 5 people who have been participating into this project, which require a lot of implementation of software implementation. So the fundamental issues are about B-level programming, multi-level programming. What is usually multi-level decisional problems arise when you are considering several players, several people who decide, who have to take decision, and which may be independent or partially independent. That means tied to each other, but some links which may be horizontal, collaborative, or hierarchical, but which keep part of the independence. And that's part of the difficulty, because it's not always very clear what we want to do in case of multi-level decision problem. Of course, if we consider that there is a kind of master of everything, above everybody, we want to find a best scenario. But in most cases, we have to take into account that the players don't follow exactly the same goals, and they don't provide each other with full information. That is part of the difficulty. So in the case where people consider the centralized paradigm, you have a lot of approaches through decomposition schemes with an issue which is the sensitivity issue about the way we may retrieve information from the different levels. But in many cases where people, well, not in the case of the centralized paradigm, things become more difficult. And the trend is to try to shortcut some of the levers. So I thought that there was an applicative context. PGMO program is a program funded by some companies in France, mainly the EDF, the main power company in France, and LabEx Immobestoire, which is carrying on a program about autonomous vehicles and solar energy. And both are interested into the notion of energy self-consumption. So what is energy self-consumption? It's an economical arising, emerging notion, which means that some people have the mean to have the possibility to produce their own energy, either through photovoltaic plant or through hydrogen microplant. And those people, they are not individual players. They are usually a group, a consortium of services operators or industrial players. And at the same time, because they produce this energy, they are consuming it. So of course, they may sell this energy on the market, or conversely, if they are not provided with enough energy, they can buy it. But the goal is to, most possible, use the energy they produce for their own consumption. And because it's most often solar energy, which depends on the sun, of course, we have to take into account both uncertainty and the fact that the cost and the production rates are time dependent. And so you have to synchronize the way you use this energy to the way it is produced. And this leads to typically a B or multi-level problem, since most often the part of the system which is producing the energy is in some way the emanation, the representation of some energy operator, while the part of the system which consumes the energy are the industrial players, the householder, or the service, the transportation service providers, and they pursue all their own goals, which may not coincide with the goal of the energy producer. So you have both uncertainty and a context where it's not very clear whether there is a leader and who is putting the rules. And here you may find some few references. There are more and more people who have been working on transportation system or production system which consider green issues. That means which try to manage the relation with electricity provider or hydrogen providers. And also you have some papers, a paper from Iranian crews, which talks about synchronization, and the paper of Wojciech, which talks about the way machine learning devices may be used in order to help decision making. So the problem, it's a simplified problem because the full problem is too complicated. So we consider an experimental problem related to the microplant, the platform, experimental platforms that the LabX IMOBIS 3 is trying to set in Clermont-Ferrand with both microplant which produce solar hydrogen through photolysis. That means clean hydrogen, which doesn't require too much electrolysis. And this hydrogen is used in order to feed autonomous vehicles. Here, the fact that they are autonomous, don't mind, we don't care with this, but the fact is that they are smart vehicles, autonomous vehicles. And on one side, you have this microplant who is provided with a limited storage capacity, which produce energy period per period, and which have to support some cost, mainly related to electrolysis, because this microplant requires some electricity in order to perform the production process. So there is an activation cost, and you have time-dependent costs, which are related to the prices of electricity on the market. And on the other side, you have a fleet of autonomous vehicles, which are powered by hydrogen. They are located at some place, let's say at a depot at the beginning, and they are supposed to perform some internal logistic tasks. That means to visit some set of stations in the order they want within a time horizon. And we know that in average, moving from a station to another one requires some time units and some energy amount. Also, the vehicles has a limited storage capacity. It starts with initial load and must end with at least the same load. Normally, we have several vehicles, and we have some kind of uncertainty about the production rates, mainly of the microplant. We don't consider it here because it would be too complicated. So we deal with one vehicles and with deterministic hypothesis. Okay. And we have to synchronize, that means we have to organize the way the vehicle works. That means mainly the route it follows, in which order it visits the different stations, and at which time it decides to refuel because of its limited storage capacity. And on the other side, we have to schedule, to plan the activity of the microplant in order to minimize the cost of the microplant, and in such a way, taking into account that the microplant has a limited storage capacity, that it will be always able to feed the vehicle with enough energy it needs to perform its trips. So part of the problem is about synchronization, mainly because of the limited storage capacity of both the vehicles and the microplant. That means one start being empty, it needs time to refuel its storage capacity, and it means this implies a kind of a waiting mechanism. Everyone has to wait for each other. And we try to optimize, and this is typical of multi-level problems, both a cost criterion which is related to the production side and a criterion which is related to the point of view of the vehicles. And now, what is the point here? We want to try to apply what we call a surrogate estimator principle. That means we want to shortcut part of the problem. Here, we consider that with the master object, we take the point of view of the vehicle fleet, the fleet manager, and we consider that we want to compute the tour, the activity of the way the vehicles organize their activity, and we want to bypass the production side. That means to replace it by some kind of approximation, but approximation has not to be taken in the usual sense. We want what we call an approximation is something which is going to give us to drive the search of a good solution for the vehicle fleet, but not automatically. It is not required to provide us with an approximation in the sense of an absolute error. So we try to replace the sub-problem induced by the fact of choosing the vehicle solution by a set of both constraints and auxiliary objective functions. It's a package which we call a surrogate estimator, and then the related the derived resolution scheme, which works as follow. And usually we put flexible parameters in order, because we are not sure of the quality of our estimator, so we want to try to introduce some kind of random effect. And why non-stop? We generate this parameter lambda, we optimize, compute the tour while optimizing the surrogate estimator, the value of the surrogate estimator, and satisfying meeting the related additional constraints. And at the end, we consider the best solution, the best true solution of our global problems. That means only at the end, we try to resolve the whole, once we have been deciding some tour, we try to resolve the whole production problem. And of course, there is a risk we don't find any feasible solution, because it's not very easy to determine which kind of constraints have to be added to the estimator. So we propose here two approaches. The first one, we have two ways of, there is not a theoretical framework in order to provide guidelines to the way we may design those surrogate estimators, but basically you have two ways to think about it. The first one is trying to define some formulas which are going to approximate the value of the problem, or to approximate some constraints. It is what we are going to see just after this. And another one is to try to design an auxiliary problem. That means what we call an implicit approach. That means we we determine the value and the torque gamma of the master object gamma, and if it satisfies some the good restrictions, the good constraints, while solving a kind of simple auxiliary problem. Here, this auxiliary problem is really simple. We try to design our tool in such a way it minimizes, it can be decomposed into feasible subtrips. That means which don't require more energy than the vehicle capacity, and which minimize some combination of time and energy. Of course, once again, we have to notice that the optimal value of this auxiliary problem doesn't need to be an approximation of the optimal value of the production subproblem. It's only need to give us some hint about what would be a good solution, a good strategy for the vehicle side. So I don't enter into detail. This auxiliary problem can be solved in polynomial time, even from the parametric point of view. It's a kind of short path problem in ad hoc network. And then we get two ways to use it. The first one is an exact one. That means we may set integral linear program which we are going to solve through branch and cut. This auxiliary program means computing a tool with an additional constraint which we call strong no subtool, and which are going to guarantee to make sure that we may decompose the tool into a sequence of subtool. We don't require more energy than the capacity of the vehicle. So there is a small theorem about it. Okay. And another way to solve exactly the same problem is because an branch and cut applied to an integral linear program may be time consuming. So is to apply a large neighborhood search algorithm, very simple, which works on the tool through insertion and removal operators. Here you see on the drawing the sequence of the subtools. The first one doesn't require more than the initial load of energy, which is contained into the vehicle. Next, the intermediate one don't require more energy than the capacity of the vehicle. And at the end, we must be able to end with at least the same amount of energy as we started.
Alain, 1 minute left, please.
Yes, okay. And the second approach is by using machine learning. That means we replace the subproblem by a neural network, which works like conventional convolutional neural networks. So the principle is simple. We first enter the production data, we normalize them, we compress, and we have several hidden layers. The idea is that we may apply instances of our problem with very different size to a neural network with fixed size, and we don't require to learn too many coefficients, because we know that the most coefficient we have to learn, and the less stable becomes the neural networks. So here is a drawing of the neural networks. As for the numerical instance, numerical experiments, we try to design instances with characteristics, with flexible characteristics, in such a way we may identify difficult instances with the need of frequent recharge and recurrent transactions, and a kind of pressure on the feasibility, on the cost. And also we try to design our instances in such a way they are realistic in the sense that they follow the way prices and the production rates may evolve during real day. So I don't enter into details. We perform a numerical experiments where we try to compare with benchmark reference, couldn't obtain the true exact result for the global model because it was too difficult, but we get lower upper bound through resolution through with CPLEX. And next, we try our different resolution scheme. The 2, 3, 4, and 5 are about the first approach and the parametric approach, and the last one, WML, is about machine learning. And we see that the first one with parametric approach works usually very well. The machine learning approach induces some error gap, between around more than 5%, between 6–7%. It's not that important because we know that when we deal with uncertainty or collaborative context, the matter is not to reach exactly an exact theoretical solution, but more to arrive to a good solution. And our next prospects are to try to go further, particularly with machine learning, the machine learning approach, because of its genericity. It can be applied to very different contexts and to very different algorithmic scheme. And also it can be applied, it's probably well fitted to deal with uncertainty or with incomplete information due to collaborative context. Okay, I thank you. And I hope I was not too long.
No, it's perfect. Thank you very much. Are there questions from the audience? Alain, I don't remember if I told you in Rennes, we had one of these autonomous vehicles going around in the campus before COVID.
Ah, yes.
Yeah, I told you already.
Yes, absolutely.
It's
okay, just it's a big trend now. Or almost everybody, at least in France, is working on this.
Yeah. We also, I think, in Rennes, we have some teams working on this.
Yes, in Ria is a big place on this.
Yeah. Unfortunately, when the COVID arrived, the lockdowns and so on, this vehicle disappeared because it's small and so not really COVID friendly. And for the moment, it's not back. But sooner or later, it was interesting because our campus is not huge, but with this small vehicle, we could just jump and especially when it was raining and not good weather, could go on the other side of the campus to the restaurant, for example.
We have the same vehicles in Clermont-Ferrand. The fact is that it's difficult to know exactly what will be the future of the vehicles. Sometimes I think they are oversold. That means they are far from being able to run in real time in a real city among the people. Maybe in the future, but just know there are some technological gaps. But when it comes to the possibility of using them inside protected area, I think they are going to find their place.
Yeah.